In the last few videos, we talked about how to do forward propagation and back propagation in a neural network in order to compute derivatives. But backprop as an algorithm has a lot of details and can be a little bit tricky to implement. And one unfortunate property is that there are many ways to have subtle bugs in backprop, so that if you run it with gradient descent or some other optimization algorithm, it could actually look like it's working, and your cost function j of theta may end up decreasing on every iteration of gradient descent, but this could hold true even though there might be some bug in your implementation of backprop. So that it looks like j of theta is decreasing, but you might just wind up with a neural network that has a higher level of error than you would with a bug-free implementation, and you might just not know that there was this subtle bug that's giving you worse performance. So what can we do about this? There's an idea called gradient checking that eliminates almost all of these problems. So today, every time I implement a backpropagation or a similar gradient descent algorithm on a neural network or any other reasonably complex model, I always implement gradient checking. And if you do this, it will help you make sure and sort of gain high confidence that your implementation of forward prop and back prop or whatever is 100% correct. And in what I've seen, this pretty much eliminates all the problems associated with sort of buggy implementations of back prop. And in the previous videos, I sort of asked you to take on faith that the formulas I gave for computing the deltas and the d's and so on, I asked you to take on faith that those actually do compute the gradients of the cost function. But once you implement numerical gradient checking, which is the topic of this video, you'll be able to sort of verify for yourself that the code you're writing is indeed computing the derivative of the cost function j. So here's the idea. Consider the following example. Suppose I have a function j of theta, and I have some value theta, and for this example, I'm going to assume that theta is just a real number. And let's say I want to estimate the derivative of this function at this point, and so the derivative is equal to the slope of that sort of tangent line. Here's how I'm going to numerically approximate the derivative, or rather here's a procedure for numerically approximating the derivative. I'm going to compute theta plus epsilon, so value a little bit to the right, and I'm going to compute theta minus epsilon, and I'm going to look at those 2 points and connect them by a straight line, and I'm going to connect these 2 points by a straight line, and I'm going to use the slope of that little red line as my approximation to the derivative, which is the true derivative is the slope of that blue line over there. So it seems like it would be a pretty good approximation. Mathematically, the slope of this red line is this vertical height divided by this horizontal width. So this point on top is j of theta plus epsilon. This point here is j of theta minus epsilon, so this vertical difference is j of theta plus epsilon minus j of theta minus epsilon, and this horizontal distance is just 2 epsilon. So my approximation is going to be that the derivative with respect to theta of j of theta at this value of theta, that's approximately j of theta plus epsilon minus j of theta minus epsilon over 2 epsilon. Usually I'll use a pretty small value for epsilon and set epsilon to be maybe on the order of 10 to the minus 4. There's usually a large range of different values for epsilon that work just fine, and in fact if you let epsilon become really small, then mathematically this term here actually mathematically becomes the derivative, becomes exactly the slope of the function at this point. It's just that we don't want to use epsilon that's too small, because then you might run into numerical problems. So I usually use epsilon around 10 to the minus 4, say. And by the way, some of you may have seen an alternative formula for estimating the derivative, which is this formula. This one on the right is called the one-sided difference, whereas the formula on the left, that's called the two-sided difference. The two-sided difference gives us a slightly more accurate estimate, so I usually use that rather than this one-sided difference estimate. So concretely, what you implement in Octave is you implement the following. You implement code to compute grad_approx, which is going to be our approximation to the derivative as just this formula, j of theta plus epsilon minus j of theta minus epsilon divided by 2 times epsilon. And this will give you a numerical estimate of the gradient at that point. And in this example, it seems like it's a pretty good estimate. Now, on the previous slide, we considered the case of when theta was a real number. Now let's look at a more general case of when theta is a vector parameter. So let's say theta is an Rn, and it might be an unreal version of the parameters of our neural network. So theta is a vector that has n elements, theta 1 up to theta n. We can then use a similar idea to approximate all the partial derivative terms. Concretely, the partial derivative of a cost function with respect to the first parameter, theta 1, that can be obtained by taking j and increasing theta 1. So you have j of theta 1 plus epsilon and so on, minus j of this theta 1 minus epsilon and divided by 2 epsilon. The partial derivative with respect to the second parameter, theta 2, is again this thing, except that you take j of, here you're increasing theta 2 by epsilon, and here you're decreasing theta 2 by epsilon, and so on, down to the derivative with respect to theta n would be if you increase and decrease theta n by epsilon over there. So these equations give you a way to numerically approximate the partial derivative of j with respect to any one of your parameters, theta I. Concretely, what you implement is therefore the following. We implement the following in octave to numerically compute the derivatives. We say for I equals 1 through n, where n is the dimension of our parameter vector theta, and I usually do this with the unrolled version of the parameters. So theta is just a long list of all of my parameters in my neural network, say. I'm going to set theta plus equals theta, then increase theta plus the ith element by epsilon, and so this is basically theta plus is equal to theta except for theta plus I, which is now incremented by epsilon. So theta plus is equal to theta 1, theta 2, and so on, and then theta I has epsilon added to it, and then I go down to theta n. So this is what theta plus is. And similarly, these two lines set theta minus to something similar, except that this, instead of theta I plus epsilon, this now becomes theta I minus epsilon. And then finally, you implement this, grad approx I, and this will give you your approximation to the partial derivative with respect to theta I of j of theta. And the way we use this in our neural network implementation is we would implement this for loop to compute the partial derivative of the cost function with respect to every parameter in our network. And we can then take the gradient that we got from backprop. So dvec was the derivatives we got from backprop. So backpropagation was a relatively efficient way to compute the derivatives or the partial derivatives of our cost function with respect to all of our parameters. And what I usually do is then take my numerically computed derivative, that is this grad approx that we just had from up here, and make sure that that is equal, or sort of approximately equal, up to small values of numerical round off, that this is pretty close to the dvec that I got from backprop. And if these two ways of computing the derivative give me the same answer, or at least give me very similar answers, up to a few decimal places, then I'm much more confident that my implementation of backprop is correct. And when I plug these dvec vectors into gradient descent or some advanced optimization algorithm, I can then be much more confident that I'm computing the derivatives correctly, and therefore that hopefully my code will run correctly and do a good job optimizing j of theta. Finally, I want to put everything together and tell you how to implement this numerical gradient checking. Here's what I usually do. First thing I do is implement backpropagation to compute dvec. So this is a procedure we talked about in the earlier video to compute dvec, which may be our unrolled version of these matrices. Then what I do is implement numerical gradient checking to compute grad approx. So this was what I described earlier in this video in the previous slide. Then you should make sure that dvec and grad approx give similar values, let's say up to a few decimal places. And finally, and this is the important step, before you start to use your code for learning, for seriously training your network, it's important to turn off gradient checking and to no longer compute this grad approx thing using the numerical derivative formulas that we talked about earlier in this video. And the reason for that is the numerical gradient checking code, the stuff we talked about in this video, that's a very computationally expensive, that's a very slow way to try to approximate the derivative. Whereas in contrast, the backpropagation algorithm that we talked about earlier, that is the thing we talked about earlier for computing D1, D2, D3, or for dvec, backprop is a much more computationally efficient way of computing the derivatives. So once you've verified that your implementation of backpropagation is correct, you should turn off gradient checking and just stop using that. So just to reiterate, you should be sure to disable your gradient checking code before running your algorithm for many iterations of gradient descent or for many iterations of the advanced optimization algorithms in order to train your classifier. Concretely, if you were to run numerical gradient checking on every single iteration of gradient descent, or if it were in the inner loop of your cost function, then your code would be very slow because the numerical gradient checking code is much slower than the backpropagation algorithm, than the backpropagation method, where you remember we were computing delta 4, delta 3, delta 2, and so on. That was the backpropagation algorithm. That is a much faster way to compute derivatives than gradient checking. So when you're ready, once you verify the implementation of backpropagation is correct, make sure you turn off or you disable your gradient checking code while you're training your algorithm, or else your code could run very slowly. So that's how you take gradients numerically, and that's how you can verify that your implementation of backpropagation is correct. Whenever I implement backpropagation or similar gradient descent algorithm for a complicated model, I always use gradient checking, and this really helps me make sure that my code is correct.